Before getting into the calculus part of polar coordinates, let's continue by reviewing some common polar graphs, starting with circles. This first graph is perhaps the most intuitive because as the angles increase, the r value remains the same, or constant, because this is an r equals constant, any constant value graph. These next two graphs are perhaps a little bit less intuitive, but let's compare them to their respective graphs on the Cartesian plane. Starting with sine x, its graph begins at the origin 0, 0, and on the polar coordinate plane, it begins at the pole. As the x values increase to pi over 2, the y value increases to 1. Similarly, as the angle increases to pi over 2, the r values increase to 1. As the x values increase to pi, however, the y values go back to 0. And similarly, the graph approaches the pole as the angles approach pi. At this point, the graph on the polar coordinate plane has already made its first revolution, which is why the domain goes from 0 to pi in both r equals a sine theta and r equals a cosine. However, since the y values become negative from pi to 2 pi, the r values also become negative. So that's why you don't see any part of the polar curve in the third and fourth quadrants, because at this point, the r values begin to swing over to this side and start a second revolution from pi to 2 pi. These polar graphs are called rose curves. Graphs of the form r equals a sine n theta, where n is odd, have n petals and y-axis symmetry, while rose curves of the form r equals a sine n theta with n being even have two n petals and y-axis symmetry and x-axis symmetry. Similarly, graphs of the form r equals a cosine n theta, with n being odd, have n petals and x-axis symmetry, while graphs of the form r equals a cosine n theta, with n being even, have two n petals and not only y-axis symmetry, but also x-axis symmetry. And the reason why this occurs is that when n is an odd number, the points in each petal are actually traced twice, from 0 to 2 pi. However, when n is even, the petals are only traced. Polar graphs of the form r is equal to a plus or minus b sine theta, or r is equal to a plus or minus b cosine theta, are called Limousin curves. When a over b is less than 1, the Limousin curve has a loop. This inner loop happens when its graph on the Cartesian plane intersects the x-axis, so it kind of accounts for that region below the x-axis on the Cartesian plane. The next graph is called a cardioid, which occurs when a over b is equal to 1. The curve on the Cartesian plane does reach the x-axis and merely touches it, accounting for the cardioid shape, which is named because of its shape similar to a heart. Next is a dimpled Limousin, which occurs when a over b is between 1 and 2. And a convex Limousin occurs when a over b is greater than or equal to 2. These two cases occur when the graph on the Cartesian plane does not reach the x-axis, so the curve doesn't even reach the pole.